Okay, so we got about what? Almost a minute, a little over a minute and a half until we get started. I might just see what I can do in that minute and a half. Need to be able to see a clock though somewhere. If I can see this one. Okay, that'll work. Resume. Oh, yes, I got a full minute. Okay, let's see what I got here. 315. Is there a 135 or 35? I don't see one. I know we had a lot of discoveries last time. I hadn't looked at this since last time either. Okay, nope. Okay, that one's already done, but there's one. So this can't be a 4. One of these have to be 4. At least we made some progress. So I got 30 seconds. Doors open, bed made. Come on. 5. Oh, yeah, this one can be a little bit tricky. We'll do our best. 6. All right, I'm not seeing anything immediate. All right, 10 seconds. All right. Just let me quick glance at 9 since I'm here. I don't see anything immediate. Okay. All right. And I have that it is that time. Might have to be taking some official attendance. People are not here. Oh. All right, we're gonna let it be for now. I might now see what I used to do once upon a time. You see how at 6 o'clock you see who's here. If I start noticing people coming in later and later, I'll lock out the meeting like at the 15-minute mark, right? If I have to be here within the first 15 minutes, you need to be here within the first 15 minutes. So like that's what I mean. As long as people are showing up and kind of being chill, I'll make a big deal about it. But once we start doing things like this and people not showing up, then I start to like, okay, it's probably too late at that point. But then I was like, okay, let me dial this back and get some of these stragglers, right? Okay. Anywho, but I'm in a good mood, so I'll try to stay in a good mood and keep it going. So, all right. So we kind of did a makeup lecture last time. We did like 3-3 and 3-4. We did the best that we could. It was, we did what we could together, and then whatever we don't do together, I do expect you to use my recordings. So today is going to be a little bit similar. Usually section 3.5, we devote the whole lecture to it, but just because of the dynamic of everything, we got to make it up. You know what it is? I know exactly what it is. It's because it's spring break. All right. So I might have to do something. We're going to see it depends on what the numbers look like at the end of class. If people aren't here, then I'll try to do something for the people that are here. I mean, this is a remote course. It's not that difficult to show through. Let me not launch it today. Because I'll make myself upset quick, fast, and in a hurry. All right. It's like, even if you're on the road, just at least just log in and just suppress the audio. All right. So at least I know that you're alive. So anywho, but we'll see what it's looking like, what the numbers are looking like. So today again, normally we do 3-5 in a full lecture. We're gonna have to half the lecture is 3-5 and half is 3-6. So what that means is that there's gonna be a good amount that I'm gonna expect you to use my recordings to get through it. You're gonna have to use that, take notes on your own. Hey Google, set an alarm for 6:35 p.m.
There, your alarm's set for 6:35 p.m.
I swear she had that thing activated before I finished my sentence. So anyway. Okay, I can't think of anything else. Let's just kind of hop into it. Let me see. So we are rapidly. So today we'll do our best to get through 3-5 and 3-6. Again, whatever we don't finish together, I do expect you to use my recording. And then obviously next week we have a spring break. So, I know when I was a student, I was already on the road. I would be one of those students visiting Wednesday. Sometimes even as an adult. But I mean, I feel like the trade-off in this day and age, because I'm remote, even if I were traveling, I would at least make it a point to show up, right? To a remote course. You know what I mean? Even if I were traveling, I would try to make it so that I can at least log in and then, and I still might travel actually. I might just hop on the road and go somewhere. So we'll see. I can't think of anything else. Yeah. So we'll have spring break next week. We come back. We'll have 2 more sections in chapter 3, and then we will be ready for the final chapter. Chapter sounds like a movie or something, right? So like business calculus, the final chapter, in a world, something like that. Anyway. So, and then once we finish chapter 4, we'll be ready. That'll be it for the semester, right? We'll take exam 2. We'll do a couple of review sessions, and then we'll take the final, and then that'll be it, right? So I honestly feel like the hardest, we're over the hump, like essentially. I feel like the hardest part has come and gone. So now it's, just kind of crossing your T's and dotting your I's, basically. All right, I guess I got to back out of this and do like this. Let's try again. All right. There we go. All right. And yeah, if you have questions, feel free. Welcome. If you have questions, feel free to either unmute yourself or type in the chat. Okay. All right. Okay, I think if I remember, I'll do it. I'm not going to say anything, but if I remember, I'll do it. Okay. Yeah, if you have questions, feel free to either unmute yourself or type in the chat, and I will make sure to get your inquiries addressed. All right. Let's see. So 3.5 optimization, right? Business, economic, and general applications. So objective solve optimization max and min problems using calculus, right? So this one is reasonable. It's fun. It's just basically applications of all the things that we've been talking about to like finance, measurements, field survey, all sorts of things like this. Like, so Loki, I went to this talk on Morehouse campus last night about real estate. I was like, it was one of the professor series. I don't know what it's called, but it was interesting. He was like, look, we're just here to make money. And I was just like, yo, it was really interesting. Like, and just some of the techniques and ways, and like he described a way where this woman, she didn't own any property. She just had the gift of gab. She was just in the right place at the right time with the right mindset. And she was like, okay, she knew how to negotiate. And just being there and talking, she was able to like walk away with like $40,000 in that session. She made more just talking with people and positioning herself than he did on whatever transaction he was doing, like selling some property or buying some property or something like that. So it's really, really interesting. Like that's one of the things that's just like, so I love about numbers. Like it's universal, and like one of the best experiences when it comes to numbers is money and finance, right? When you start to see your bank account, when our bank accounts are growing exponentially and we're getting passive and residual income and big payouts, I don't know how you can be somebody to say you don't like math, you don't like numbers. Then just give your money to me. Just give it to me and I'll appreciate it. You know what I mean? So anyway, they go hand in hand. Okay, so let's hop on into this. Okay. All right, so a strategy for solving max-min problems. Read the problem carefully. If relevant, make a drawing. Make a list of appropriate variables and constants, noting what varies, what stays fixed, and what units are used. Label the measurements on your drawing if one exists. Translate the problem to an equation involving a quantity Q to be maximized or minimized. Try to represent Q in terms of the variables in step 2. Then try to express Q as a function of one variable. Use the procedures developed from sections 2.1 to 2.3 to determine the max or min values and the points at which they occur. Okay, so just some suggestions on how to solve max-min problems, right? So let's look at this example. From a thin piece of cardboard, 8 inches by 8 inches, square corners are cut out of the size they can fold up to make a box. What dimensions will yield a box of maximum volume? And then what is the maximum? Okay, this is a fun one. I like this one. Okay, grab this, and I think I would like to give myself a little bit more space. So what I am going to do is duplicate this guy. Duplicate. Actually, not that. I don't want that slide. Delete. This is slide. I needed to be slide just after slide 6. It'd be nice if I can copy this. This is what I really want. If I can paste it right there, it's looking good. God is good. Okay. So now what I need from here is a screenshot, a reference. Another thing that was interesting about the gentleman from last night, he was like, I'm not a professor. He was like, he's just been doing this business for over 30 years, so he just knows everything. So he's like, kind of like one of the old heads. They just know how to talk. And I mean, he knows what he's talking about. I was like, man, this is interesting. Even just from a pure numerical sense. But again, one of my favorite ways to experience numbers is an increase in finance, revenue, whatever. Because then you can start to do things that you love to do, travel and eat and explore and adventure and really live this life the way I think it's supposed to be experienced. Okay, so it sounds like we're starting with a square piece of cardboard. So I'm going to draw a picture. I'm going to start with the picture and do my best to get a square. Boom, that is the square, okay? And then it says that, it says a piece of cardboard that's 8 inches by 8 inches. So like, for instance, this is 8 inches. And so the way you see me taking my notes now during lecture, this is the same thing I was doing during his lecture. I took my same tablet. I just did an audio recording. I was able to acquire a digital copy of his PowerPoint at the start. So I just loaded it in here the same way I do my presentations with you all. This is what I did in grad school. And that's what I did last night. So I got an audio recording that matches up with his PowerPoint, my notes. So, I mean, this is just an iPad and I'm using Notability. But yeah, I have like notes from grad school and, it's good stuff, right? So we have a square piece of cardboard that's 8 inches by 8 inches. Then it says that we cut out square corners so that the edges can be folded up. So I'm going to duplicate this. I'm going to shrink this down. We'll say the corner is about like this. I'll go style. I want this to be like, nope. Fill, I want the fill to be none. Stroke to be this. Okay. Let me see. Let me duplicate this. Duplicate. And so basically we're cutting out square corners. Duplicate. I could change the color to brown. Let me see. Can I like cut, and then paste? Put it back. Because I kind of want that to be on top. Perf. That's exactly what I want. Right? So we're starting with a square piece of cardboard. Let me duplicate this as well. Like right there. Style. Black and dash like that. Okay. What dimensions will yield a box that maximize? We want to maximize the volume, right? So we're cutting off these squares, but we don't know like how big this square is, right? So let me see. For instance, this distance is X inches, right? From here to here. So, that's X inches, and that's all over, it's a square. Okay. So, that tells us how the length of the side of the square that we're going to cut out. So then when we cut it out, right? Let me move this over to about here, I guess. It's kind of in the way. Let me kind of move this around. And that's okay. I can work with that. Okay, we got that there. I'll put you there. Okay. So then when we cut out those squares, I'll highlight them like this. These are my colors. Okay, I can't add anymore. Let's change this. That's the one I don't use. It's just too bright. Right here. Okay. So let me see. Yeah, we're gonna. I just want to be clear that I'm removing those guys, right? So when we cut those guys out, then we're going to get an image like the following. So we have that. Let's duplicate that. And we're making a 3D box. I'll go about, I guess about here, right? And then that's decent. That's decent. That's decent. That's decent. I'm just being a little bit meticulous just because. Okay. So we want to cut like that, like that. Let me see what else I can get to work. Style. Yes, that is correct. Style. Right. So those dashed lines are because that's inside the box, right? It's behind the wall, the front wall and the right wall. So we have a flat piece of cardboard that's 8 inches by 8 inches. We cut out we cut out the square corners, the squares from the corners of the cardboard. We fold up the flaps and we get an image like we see on the right, where it's basically a 3D box. So from in the perspective of the box, right? This side over here, this will be our X inches here, from here to here. Okay, so this base here, that base is going to be 8 inches minus 2x. 8 minus 2x inches from here to here. Hopefully that makes sense. And I think it's the same thing over here. 8 minus 2x inches from here to here. Right? And, you know, because again, if that's X inches, this is X inches from here to here. So then that middle is going to be what? 8 minus 2x. 8 minus 2x inches from here to here. Right? And so in the 3D box, we get an image like what we have on the right. So, okay. So what dimensions will yield up? We want to maximize the volume. Right? So our goal, we want to maximize the volume, right? And so the volume of a rectangular prism is going to be what? Length times width times height. Okay. So then if we keep going, that's going to be what? X times 8 minus 2x. This needs to be a minus. Times 8 minus 2x. Okay, and again, our goal is to maximize the volume. Hopefully this makes sense, right? So notice we have, well, essentially one equation and one unknown. All right, so let's expand this guy, right? And this is the volume based on x. So we'll call it V of x. Okay. So then if we keep going, we're going to have x times, if we FOIL, 64, double, let's see, 1632, outer 16 to 16 negative 32. So minus 32x and then plus 4x squared. I just FOILed those second two, and then I'm going to distribute that x. So again, our goal is to maximize our volume based on x, which is going to give us, I'm going to put it in descending power order. I'm going to distribute my x here and put it in descending power order. So the volume based on x is going to give us 4x cubed minus 32x squared plus 64x, right? We want to maximize this guy, okay? So notice we have a cubic function. So we would anticipate our leading coefficient is positive. So from college algebra, is that college? I think it's college algebra, right? A positive leading coefficient means what? We would anticipate our graph of this function to go up to the right. The degree of the polynomial is odd, so the other side does the opposite, so it falls to the left. So it should go up to the right, fall to the left. We would anticipate maybe one relative max and one relative min potentially. So now we can use the first derivative test, second derivative test to identify the local max and min. So let's look at the derivatives. The first derivative, and potentially the second derivative if it's simple enough to find, right? So then our v prime, our first derivative, is what? 12x squared minus 64x plus 64. And just for, just for the sake of it, let's go ahead and take a look at the second derivative. So that's a 24x minus 64. Okay. So we have the first derivative and second derivative. If we want to maximize the volume, the max of the original graph is going to occur at the critical values of the first derivative. That's where the first derivative is either what? 0 or undefined. Can we find that 0? Let me see. Can we? It's not. We can't factor out 12. We might be able to factor out a 4. What is that? 24 is a 16. Okay. So if we set the first derivative to 0 and solve, it looks like we can factor out a 4. We're going to have a 3x squared. I think that was a 16. 40 plus 24. X plus 16 equal. We want to set this to 0. Can we factor this guy? Okay. So I'm going to do some work over on the side. What is that? 30 and 18, 48. So I'm looking for two numbers that multiply to give me what? 48 and add up to negative 16. Now 48, we got what? 3 times 16. Okay. So 16 is what? 2 times 2 times 2 times 2 and then times 3, right? So we're going to go through all the factors of 48 and stop at the line that adds up to negative 16. Okay. So 1 and 48, but those don't add up to the right thing. So then we can do what? 2 and what? So if we've used the 2, 8 times 3 is what? 24. So 24 is left over. But that adds up to 26. Can we do a 3? Yeah, we can do a 3. If we've used this 3 already, we have what? 16 left. That adds up to 19. We're almost there, right? We're looking for two numbers that add up to negative 16. We can do a 4, right? If we've used this 4 already, 4 times 3 is 12 is left over. Notice that 12 and 4 adds up to positive 16. So we want negative 16. So then our two numbers are negative 4 and negative 12. Okay. So these are the two numbers that we were looking for. The rest of these was just part of the journey. Okay. So back to our factor. Okay, so we got this 3x squared. Let me see. I'm going to put the 4 next to the 16. Nope. Yeah, that's fine. All right. So we're going to rewrite that negative 16 using the two numbers that we just found. So we found a negative 12, negative 12x minus 4x. And again, what we just did was rewrote this. Come on. There we go. Man, this is eating up a lot of time. What time is it? It's almost time for the next section, so we're not going to have time to go through another example. Dang, and these are a lot of fun. Like, I really enjoy these. I low-key would just rather this and just bypass the next one, but it's okay. All right. So then I'm going to use factor by grouping. Right, I'm using factor by grouping. We got 4 more terms. So from those first 2 terms, look like we can factor out a 3x. Right. If we do that, we're going to be left with x minus 4. So the trick is we're anticipating another x minus 4 over here. Looks like we can factor out what, a negative 4 from those second 2 terms. All right. Negative 4x, positive 16. And then we got this parentheses. Okay. So then now we factor out the common binomial factor. I kind of want to move this around, but what I'll do, I'm going to duplicate this and get rid of the excess. I'm just trying to pick up where I left off. Delete. I think that's good. Hope I didn't get rid of something. I think we're okay. Okay. Delete, and I'll just move this to the top over here. This is where we left off. Okay, that's fine. Okay, So now we can factor out the common binomial factor. But then we're going to have this 4. We're going to factor out this x minus 4 from both terms, and we're left with 3x minus 4, okay, equal to 0. Okay, so that might have to kind of jump back. Let me see. So this is the factor of v prime. So we were trying to find the critical value. So now that we have it in fully factored form, from here we get that our candidate for our critical values are what? We got 4 over 3. X equals 4 over 3 or 4, right? These are our candidates for our critical values. So now we need to do like our first derivative test to determine if these are max or mins. We could plug these into the second derivative, like for instance. So if this is our positive x, right? Here is the 4 over 3. Here is the 4, right? We were considering the first v prime. We were also considering v double prime. Let's start off by plugging in the 4 over 3 into the second derivative. 4 over 3, ultimately that's going to, let me see. 24 divided by 3 is 8 times 4 is 32. That's going to be negative, right? If we plug in 4 over 3 into the second derivative, it looks like we get a negative result. So that 4 over 3 is negative in the second derivative. That implies that the original function is concave down. I'm pretty sure there's a little bit more we need to do there, but that's essentially what it's telling us. Let's see what happens if we plug, which means that, that has a lot of implications. Let's see what happens when we plug 4 into the second derivative. I think we get a positive, right? That's 80 plus 60, and 96 minus 60 is positive. So when we plug 4 into the second derivative, we get a positive result here, which implies the original function is concave up. Now, we could evaluate, that's essentially the second derivative test, right? If we wanted to use the first derivative test, remember these guys were 0 in the first derivative. We would have to choose a test value in region A, choose a test value in region B, choose a test value in region C, right? If you choose something in region A and plug it into the first derivative, you should get a positive result, right? You should get a positive result, which implies the original function should be increasing. If you choose a test value in region B, you should get a negative result, which implies the original function is decreasing. If you choose a test value in region C, you should get a positive result, which implies that the original function is increasing, right? And let's just do a few test values just to confirm that. So a simple number in region A to test is when x is 0. So if we plug 0 into the first derivative, I'm going to go back, we get a positive result like we anticipated. Let me see, that's what, 1 1/3. So if we chose 2 would be in region B. If we plug 2 into the first derivative, we're expecting a negative result. Let's see. 4, it looks like it's negative. All right, 48 minus 128 is negative. It's ultimately going to be negative, right? So we did get our negative result for a number in region B into the first derivative. And then we choose a test value in region C to plug in the first derivative. Something like 5, we should get a positive result. And I'm pretty sure that one works too, right? Okay. Oh no, 10 minutes, okay. Yeah, so I called IT. It's gonna cut off on us. When it does, I'm just gonna log right back in and my videos are just gonna have to be broken up. So when it boots us out, I'll just log right back in. We might even go into the next section. Let's try to wrap this one up. I don't like to be interrupted like that, but it's out of our control, and it will get resolved because there's something on there. But anyway, right? So with this, we're getting that we get a local max. Let's use this color to get some pop. We get a local max here, and we get a local min. We get a local minimum value here, or a relative max, relative min, right? But we want to maximize the volume. So our claim is that the volume is maximized when x is 4/3, right? And then we can find the maximum value by take that x value, plug it into the original function. It'll give us the max volume. Let me see, what dimensions will yield? Okay, so our claim is that when x is 4/3. Okay. And then what is the max volume? Okay. So the dimensions, so for part A, I know it's a little bit jammed. I'll just put this up here now. So for the first question, if X is 4/3, 4/3 of an inch, by 4/3, 8/3, 24/3, 16/3. Looks like it's 16/3 inches by 16/3 inches. And then the maximum volume, you just multiply those. I don't know. Hey, Google, what's 4/3 times 16/3 times 16/3?
4 divided by 3 times 16 divided by 3 times 16 divided by 3 is approximately 37.93.
Hey, Google, what's that as a fraction?
I don't understand.
All right.
But I found something else. Do you want to know what it is as a fraction?
Yes.
Sorry, I don't understand.
Okay. Hey, Google, what's 4 times 16 times 16?
4 times 16 times 16 is 1024.
3 and 4 is a 7. 12 is a 4. And then there's a 1 and a third. That can't be right. I think I made a mistake. The volume, 341 cubic inches? It could be. Let me check over here. I mean, that could be. Inches cubed. I know it's about to cut off. Okay, so these are the results that I got. I got these dimensions with that volume. I'm gonna go with it just for the sake of time. Okay, let me kind of glance here. So I think we got the setup. I just want to see the final answer real quick. 37, 4/3, 37. I think I just did that final calculation incorrectly. So we got the answer correct. We got that volume. We got to fix it though. Let me check here again. Let me just redo it. Give me a second. Oh, shyster. Okay. Whole. There we go. Okay. Let me see. 3 into 10 is a 3. 12. Something is not right there. Oh, we got to multiply the denominator. I forgot to multiply the denominator. That's what I'm missing. Right here. So that needs to be what, 27? So I was like, I knew something was off. So about, let me see. If there were 25, it would be a 4. Let me see. 80 plus 28. It's about 3. 60. I don't know. What's that? What's 3 times 27? 60 plus 21 is 81. So 19 has a remainder. So that's 19. 194. Must be, I know it's a 7. 194 times 2. 140, 168. I'm trying to do this in my head. Anyway, I just need to write it. I know it's one part missing. 25/27. Okay, I'm gonna go with it. I know we're there, and I'm just rushing, trying to beat this timer. We'll be back. So again, when it cuts off, I'm just gonna log right back in, and we'll probably go ahead and move into the next section. Let me try to scan here, but I think we got everything. We got a few calculations there toward the end, but everything else was good. Okay. I'm just trying to beat the clock at this point. Inches cubed. Come on. Okay, that's fine. Google was, anyway. All right, so I'll leave this as an exercise, and I think the rest are just examples similar to that, and just other applications. So I'll go ahead and officially close out. I don't think it's anything like relative. So for this section, whatever these remaining examples, whatever we don't finish together, I do expect you to use my recordings, take notes of your own class. I'm trying to let this like lock out, and I'm going to go ahead and hop into. I'll make a copy of this available at the end of class. I'm going to go ahead and hop into the next section because this is about that time anyway. So let me scan a little bit. But again, these are worked out in my pre-recorded lectures. They should be. Mm-hmm. Okay, yeah, it's not too terribly bad. I think that first one was my favorite one anyway. This one was a little bit tricky, but this one definitely is in my pre-recorded lecture. Okay, I'm going to go ahead and hop into the next section. Just trying to let the timer run out. I wish can I see a timer that would tell me? It's okay, I'm not seeing anything. All right. All right, I'm just gonna kind of go ahead until it cuts off. Okay. So we're continuing chapter 3 on applications of differentiation. And here we're gonna look at section 3.6, marginals, differentials, and linearization. Okay, let's look at here. So a few objectives here. One, find marginal cost, revenue, and profit. Find delta y and dy. Okay, and then use differentials for approximations. Find a linearization of a function at x equals a. So the delta, that triangle that's called delta y, that just means the change in y. So y2 minus y1 versus dy is your differential. That comes out of, that's like the y coordinate, like when we take the derivative because of the slope of the tangent line. So that's like the change in y over change in x. That change in y from the derivative is the dy, right? So that's coming up. Linearization of a function is that's how we can jump straight to the equation of the tangent line at a point. The derivative gives us the slope of a tangent line. Linearization is a formula that takes us straight to the equation of the line at a tangent at a tangent. Hey Google, stop. But we're going to get into that. All right, so as best we can. I'm just dreading it. I'm just dreading it. Cut it off of it. I'm stalling, trying to let it stop, and I can't see a timer. I don't know. We'll be back once it and I don't know, for whatever reason I'm hesitant about just turning it off and rebooting it. I want it to cut off, and then we'll be back. Anyway, so a few definitions here. Let C of x, R of x, and P of x represent respectively the total cost, revenue, and profit from the production and sale of x items. The marginal cost of x given by C prime is the approximate cost of the x minus first item. All right. So C prime is approximately C of x plus 1 minus C of x, or C of x plus 1 is approximately C of x plus C prime, right? So it's the approximate cost of the x minus first item. X minus 1, x minus the first item. That's the best way I can say it.